Hello and welcome back to the lecture on applied econometrics. We have been talking about the problem of multicollinearity. Now, we explained the concept of multicollinearity. We have also sort of given you a proof why perfect collinearity is a problem. Now, we will try to see why exactly if I have multicollinearity, I understand perfect collinearity is a problem. But if I have like imperfect collinearity, it may be high multicollinearity, low multicollinearity, why is that going to be a problem? Suppose my x variables are related, to some extent. How is that going to create a problem in my regression equation? And that is what we are going to see. The major problem, and that you need to remember, is that in case of multicollinearity, if the x variables are related, what happens is that the standard error term corresponding to each of these beta coefficients that we are estimating is going to be high. I repeat, the major problem that occurs due to the multicollinearity is that the standard error term associated with each of the beta coefficients in the regression equation are going to be high, because if there is a high multicollinearity problem. So, depending on the extent of multicollinearity, we will have different levels of standard error, right? And a high multicollinearity would lead to a high standard error, and we will see what happens if I have high standard error. So, let me first explain the standard error for the different coefficients in a regression equation, okay? And we will sort of use a result that we previously derived when we derived the relationship between B2 and beta 2. So, the sample coefficient, sample regression coefficient and the population regression coefficient. So, I will not actually derive it. So, you just look at your previous notes. So, where we derived it as B2 is equal to beta 2 plus xi minus x bar into ui minus u bar by summation of xi minus x bar whole square. So, we said that this the value of B2 is actually a sum total of a sort of non-stochastic component and a stochastic component because of the involvement of the error term here, and that is what actually gives a distribution for the B2 that we determined, right? Now, if I further simplify, so I am not going to show you the full proof. You can again find this proof in Christopher Dougherty's textbook, chapter 3. It is going to be, so because you can take like it is actually going to be xi minus x bar into ui by summation xi minus x bar whole square, all right. Now, if I actually use this relationship, I can actually write, let us say, simplify it as beta 2 plus summation of ai ui, this one. And if I use this value of B2 here, and if I actually try to get a sigma square value for B2, what I will do is I will actually do something like this: expectation of B2 minus of E of B2, okay, and a whole square of that. So, let us say I use a third bracket here, So, this is going to be the value of my sigma square, and if I simplify it, what I will get is that, I am not going to show the steps again. So, what I will get is sigma beta 2 square is equal to, it is going to be sigma u square by xi minus x bar whole square, okay. And if I have, say, a term, let us say, if I have, so this is where I have like simple way, let's say I have only one variable x, okay. But if suppose I have two variables x2 and x3, let us say I have only one explanatory variable, but if I have say two explanatory variable, So what will happen is that because there is a correlation between these two explanatory variable, so the equation is going to be, in that case, is sigma u square by summation of x. So here I have my only variable is let's say I am trying to get the coefficient for x2 variable, right. So it is going to be x2 minus x2 bar all over I, let's say I put an I here also, over all I square into 1 by 1 minus r x2 x3 square. So where r x2 x3 is nothing but the correlation coefficient between these two variables x2 and x3. Okay. Similarly, if I have to write, say, the sigma square value for beta 3, so standard error, these are nothing but the standard error for beta 2. Okay. So this is the standard error for beta 2 and it has this formula, and similarly I can write standard error for beta 3, which is a coefficient for x3, and that is going to be beta 3 square. It is going to be variance for the error term and summation of x3i. Now my variable, the variable I am concerned is x3 square into the other term remains same, 1 by 1 minus r x2 x3 square. Okay. So essentially you see that we have basically what we are doing, we are multiplying a term in case of multiple explanatory variables. So here I have two explanatory variables. So what I am doing is that I am multiplying the term 1 by 1 minus r x2 x3 square. All right. And now let us try to understand. So this is basically the form of standard error, and again, if you want to see the proof, I would recommend you consult Christopher Dougherty's textbook, chapter 3. Now let's try to understand what is happening here. Suppose the correlation between x2 and x3 is very high. So r square value is very high. So if that happens, what will happen? So if the r square value is very high, so 1 minus r square value is going to be very low. And if 1 minus r square value is going to be very low, what will happen is the standard error of beta or sigma beta 2 or beta 3, whichever you take, that value is going to be very high, right. And if the standard error of beta is going to be very high, so I normally, if you remember a regression, how a regression looks like, so you have, I'm taking a previous regression that we have run. So this is a coefficient, this is a standard error, and this is your t value, right. So you get your, so let me actually write down the implication. Okay. So if I have, so basically my t distribution, t value is nothing but my beta 2 by my standard error of beta 2, right. So that is how we define it. Now if my standard error of beta 2 is very high, what are you going to have is very low t value, right. And if I have a very low t value, what will happen is that this t value that we estimate is going to be somewhere near here, right. T value, let's say t estimated, and it is going to be, if I have like a high standard error, it is going to be somewhere near to this mean, and that will mean that my t critical, it is going to be left to the t critical, which would mean that my t critical, so basically my coefficient is going to be, if there is a case, my beta coefficient, the corresponding B2 is going to be insignificant, right. So the problem here is that if I have high standard error, so even if my B2 is actually important, it is actually explaining the regression equation, just because of the fact that I have a high standard error, I will actually see a very low B2 value. It is going to be insignificant, right. It is going to give me an insignificant beta, not low value, but not low t value, and because of the low t value, I am going to get a insignificant beta 2 or B2. So low t value means high p value. Okay. So we will see an insignificant value for the particular beta coefficient. So if I actually run this regression equation, so let me actually go back and run this regression equation. Here I'm just going to include this ln output, ln labor, ln capital, labor and capital. Okay. So, essentially labor capital and the logarithmic two variables for log capital, log labor, these are my explanatory variables. So, if I run this, I will see that for this for labor and capital, the t values are pretty low, like 0.6, 0.67, and the p values are quite high. We know that for low t value, we will have a corresponding high p value. Now, so these two variables are going to be insignificant, and the reason here is that there is a high multicollinearity problem. So, because I have labor, capital, and at the same time, like I have log of labor and log of capital. All right. So, this is something that is going to give me a insignificant value for beta. But what happens is that because my model is well fitted, so because my variables are actually explaining the error, so my explained sum of error is actually going to be pretty high, and if that is the case, then it is actually explaining the most of the variations in the total sum of square. So, it is going to give me a very high R square. So, essentially what will happen is if the model is actually the variables are related, highly related, but again that they are actually explaining the y variable, then even if the R square value is high. So, they are actually going to give me a high R square value, whereas I will have the coefficients insignificant. Okay. So, that is basically something that we need to remember in case of multicollinearity. So, this is one symptom that we will see. A variable that I feel should be actually explaining the y variable, that is actually insignificant, but at the same time I am seeing a high R square value. Now, let me tell you a couple of more sort of symptoms of when you actually have this multicollinearity problem. So, what will happen if you add or maybe delete one variable, delete one, say x variables. What will happen is, if they are highly correlated, so what will happen is that this term here, this Rxy, this term here, this correlation coefficient term here, this is going to change because they are actually dependent on which other variables are present there, right? And if there is a high sort of correlation coefficient among the variables, so this value is going to be high. And the moment you change one variable, it is going to change, right? And the moment it is going to change, my standard error is going to change. And if my standard error is going to change, my t value is also going to change drastically. And it means by the moment you include a variable or exclude a x variable, it will automatically change the coefficients, the level of significance or the significance of the coefficients, the explanatory variables. Okay. So, that is another basically case where if you add or delete variable, you will see it's highly sensitive because it will drastically change the the values or the sign or the significance of other explanatory variable. Okay. Explanatory variables. And it can also happen if you basically bring in more data. Okay. So, if you bring in more data or if you reduce some data, so it will also be very sensitive to any sort of change. So, if you see this kind of sensitivity existing in your model, you can actually presume that there might be a problem of multicollinearity. Okay. So, these are some of the symptoms for multicollinearity, and we will just conclude this lecture by saying that usually we have used this term 1 by 1 minus r square x2 x3. So, usually this term is also referred as VIF, variance, inflation, or some books use inflation, like Gujarati use inflating, whereas Dougherty would use inflation, inflating factor. Okay. So, it's mathematically we write it 1 by 1 minus r x2 x3 square. Okay, and we will see the importance of this VIF when we talk about multicollinearity. So, with this we sort of end this particular lecture where we have explained the problem of high standard error, which is essentially the crucial problem when we deal with multicollinearity. And with this we end the lecture. In the next lecture we are going to see some other problems and how we are going to sort of remedy the problems of multicollinearity.